pressure of the gas container, okay? Or we can change the pressure of the gas container and then measure the volume, how the volume change. Both can be done, but in the simulator, it is easy if we can measure the pressure as a function of volume changes, okay? So that's what we're going to do. To check the Boyle's law. If the Boyle's law is correct, after we graph volume versus pressure, we should get inverse proportionality, right? That's what we're expecting. So the proportionality on equation number 1. Okay. All right. So now in the simulator, we are on the first option, right? So it says ideal right here. When you go into the simulator link, there's like 4 different options you can select. Out of that 4, we are on the ideal option number 1, okay? And then on your right hand side, you will see a couple of different options. The hold constant, which means we can select what to hold during this experiment, okay? And then there are a couple of other options here. We can have a stopwatch, collision counter. We don't need any of those things for first part. And we can select the particle type. There are 2 particle types, light and heavy. Nothing else can be added into here. We can't just specify the type of gas or anything. We can just say either it is a lighter atom or the heavy atom. That's all we can say there. And we can heat this by using this container below. You can see if you click this into the top or bottom, depending on that, we can change the temperature also. Okay. And then there's a thermometer here, and the temperature will show up here in Kelvin is good. That's what we wanted. Pressure of the gas container show up here. And this handle you can see right here, we can use that handle to change the size of the gas container, right? So we can go all the way to the max and then slowly decrease and then check the how the pressure changes as a function of volume change. Now, the problem with the volume, changing volume of this container, you can see I have freedom to change only one direction, okay? So we can do 2 different assumptions. The one is that we can assume this is a cubic shape. Whatever I change on this direction, change on the other 2 directions. That's one way to do it. Other way is that we can assume other 2 directions are fixed, and then we'll use those fixed numbers, and then we're using only this width right here, okay? So that's the plan. Now you can measure that width. If you click on this right-hand side middle, it says the width. If you click that, you can see a line appear here, dotted line, and it say 15 nanometers, okay? 15.0 nanometers. If you go into table number 1, that exactly we have there too, okay? So what we're going to do, we are actually changing only the width of the container. We are assuming other 2 sides are stay constant, okay? That's the plan. The all are, you know, real, all are not the real measurement. The gas container will change according to the internal parameter what the program has. We have no idea what those parameters are. That's a problem. But it doesn't matter because we're not calculating anything like specific numbers. We're just checking the proportionality. Still, we will get the right answer. Okay. So it worked fine either way. So we can assume maybe length and thickness like maybe 10 and 5 nanometers. Those numbers works better. So we can assume the same numbers. Okay. So which means you have to add the units here. We have nanometers, 10 to the power negative 9 meters. And when it go to volume now, so you have nanometer times nanometer times nanometer. This should be 10 to the power negative 27, 9 times 3, and then meter cube. Okay, I need to have the SI units. So this should be meter cube then. Okay. Question. And also you can add here a little bit of more information. For example, length and width, we keep in constant. So those actual numbers, you can see it here, okay? Length and width, we keep in constant, and the pressure, starting pressure, atmospheric pressure, and the starting temperature, we can fix that into like 300 K. Question. Okay, now to start the experiment, so you have to add the gas into here, right? We can add either heavy atoms or the light atoms. So let's try with the light atoms, right? Light atoms. To add the gases, what you have to do, click on this. You can see a pump icon right here. You need to click on this handle and then add a little bit of gases into that, okay? If you pump up and then click downward, then the gas goes inside there. Then when the gas goes inside, you can see the pressure show up and the temperature also will show up. Now, right now the temperature is 300 K. We need to fix that temperature, right? So let's fix that temperature by clicking here. Then you can see the temperature is fixed. It says the whole constant, right? So which means if I click the temperature, then during the experiment, temperature will not change. It will hold constant, and then we can change the volume and then measure how the pressure is actually increasing. Question. Temperature is fine, starting at 300. Length and thickness we assume stay constant, and then we changing only volume by changing the width, okay? And when it comes to pressure, you can see it measuring at ATM. You can change that into kilopascal. That's better because we need the Pascal unit. Since it is kilopascal, you can add the unit here. This is going to be 10 to the power 3 times the Pascal, right? Because it gives you the kilopascal. I can just write it down, that numbers coming out from that, okay? Okay, now to get the volume, if I assume length and thickness remaining constant, width right now 15, so which means I can multiply this cell by 10 times another 5, because length time width time thickness, right? So that will give you a number. Technically, it doesn't matter this number. Even if I use these numbers, still I will get the shape of the graph, okay? And the pressure at that volume is about like 300. One thing you have to do now, you can see this pressure is changing actually fairly large numbers, okay? It's not really constant. Because of that, what you have to do, you have to stop this whole simulator. If you click on this icon right here, left hand side very lower, it has a play button. You need to click that and then stop the playing motion, and then it will tell you a fixed number. So we'll extract that number, okay? Since we only trying to observing only the ratio or the proportionality, we will get that. It's still 401. And then all you have to do is change the volume, maybe by 2 nanometers at a time, by click on this handle and then bringing that towards your right hand side. Then observe this number right here on the width with this dash line. Then you can see that number is changing, and then decrease the volume until you see number 13 there. Then you can see at the same time pressure has to change, right? So look at the earlier pressure, starting pressure. And let me go back and then see what happened to the pressure. Is it changing every time when I do any changes? Yeah. Yeah, we have to, if we are in this play mode, on the pause mode, you can't really read it twice, okay? When you go in and then read the number, if you go back and then try to read the numbers, the program actually changing that numbers, okay? So we can't really do that. So what we have to do, since we try to go in this pause mode, now you starting at the maximum volume, you read the numbers and then slowly decreasing 2 nanometers at a time, and then read the number you see. Don't go backward and then come again. Then the program going to give you some random numbers. Okay, then our calculation not going to be much meaningful. Okay, so that will give you very, very different behavior. Don't go backward. Okay, only at a time, go frontward and then read the numbers. Good question. Anybody have any questions? Since I went back and forth, I have to start again the pressure value which I read. And also make sure you read the temperature must remain in constant, okay? 401. Question. Is it changing with the time? The pressure number, that also you have to take a look, okay? If it's changing with the time, that also not good, okay? You will not get my numbers at all. That's totally fine, because these numbers, I think, randomly generated. It's not anything fixed. I test this couple of times. It's not anything fixed really. And we can't really adjust with any real calculation at all. They just randomly put it up to work when the pressure decrease, what happened to the volume, and then so on. Otherwise, we can't do any real calculation at all with this, okay? 380, and then let's see if I decrease this to 30 nanometers for O1. So what I expecting is when the pressure decreasing, when the volume decreasing, pressure must increase, right? So that's what we expecting, inverse proportionality. As far as we observing that, we are okay. We don't need anything else, okay? The numbers has no any real connection to any real gases or anything either. And that's all. It's that simple. You just decrease this at a time, but don't go backward, okay? Always only click this and then go a smaller direction. If you go back and come again, then the numbers completely going to be changing, has no any meaning at all. 517 at 11, and then let's go to 9 nanometers. 567. That's what you have to keep track, because the pressure must be increasing because we're going on volume decreasing direction. That's what the Boyle's law means, right? As far as you observe that behavior, then you find 810. And last one is 5. I think that's the only smallest value you can go in the volume in the container. That is 1046 kilopascal. Question. Okay. Now let's calculate volume, right? Because since the length and thickness remaining constant, if I do one calculation with the cell values, then all we need to do is click and drag this, right? Click on the same cell, right hand side, very bottom, solid dot, green dot, and then drag downward direction. Then you can fill up automatically all the rest of the calculation. Okay. Then let's take a look two different way this behavior, Boyle's law, right? We can take a look with the PV remaining constant. That I can't guarantee, because the reason numbers may not be much meaningful in this simulator, okay? But we can check that. But definitely if I make a graph between P and V, that must show us inverse proportionality. That's what we're trying to see, okay? But let's take a look what happened to the PV, because we know if the temperature is constant, P time V must remain in constant, right? Let's check that equal sign, volume times the pressure, and then let's click and drag downward direction. It's fairly consistent. There are a couple of numbers goes a little bit off. You can see there's 2.8 and then another 2.8 here, 2.9. But other than that, if you take a look average wise, it's still very consistent. So that's what the Boyle's law tells you, right? As far as temperature remaining constant, gas volume and then pressure product should be remaining constant. So it's good. And let's make a couple of graphs, like two different graphs. We can make a graph V versus T. Let's make a graph. And also, since we do this Excel functions, you have to call them or use them during the discussion section. In the discussion section, or you should add all those functions into your appendix C. Okay. As we progress through, you can collect those functions somewhere close by the table, but don't put it into the table. That's not good. Okay. You multiply pressure and the volume. C11 times D11. Okay, let me copy paste those function. There's a function here. Let's copy paste that into here. That's for the volume. And there's another function here for the PV. Don't use this function with the table. Okay, that's not looks good on your lab report. Use these functions only during the discussion, in the discussion or appendix. Okay, appendix C. And also you don't need to add the same function again, right? Because we're doing the same function now here 6 times repetitive, right? In the table, you don't need to tell that. You need to say only one time PV was calculated by using Excel function of this. That's all. Because the same function we're doing again and again on the same table. And the units for this one, for PV. So V is in 10 to the power minus 27 meter cube, and then P has 10 to the positive 3, so which means this has to be reduced by 3, right? So this should be then negative 24, and then Pascal cubic meter, but the Pascal is actually force divided by Newton squared, so you can change these units accordingly. Okay, so let's take a look. I have Pascal. Let me write it down this first here. In terms of unit, I have Pascal times cubic meter cube. But the Pascal is actually the pressure, which means the force per area. So that means force is Newton divided by meter square, and which multiplied by meter cube again, right? Meter cube again, so which means 2 meters cancels out, then you will get Newton meters, right? So Newton meters is actually joules, correct? So you have to find the right unit accordingly, okay? Newton meter is fine, but the Pascal meter cube may not be a good way to leave the units, okay? But that's also okay, that's the direct unit you're getting by multiplication. Nothing wrong if you leave it like that. So you can say Pascal times meter cube, or you can write it down the same unit, maybe Newton meters or joule. And 1 of the 10 to the power positive 3 cancels out. This will becomes only 10 to the power negative 24. Okay, question. PV should be the work done. Okay, that's why the unit you're getting actually joule. Now you don't need to put all these unit. Okay, leave it one of them. That is better actually. Okay, good. Any question? Let's then make a graph. Let's make a graph PV. Here is the unit conversion which we done. Insert, and then in the middle right here, click on the insert on the very top. Then the charts, and then we interested scatter plot always. Okay, chart and scatter plot. And then let's add the data. Double click on the graph, select data, click on add, left hand side corner. Then you will see this new window, and then click on the X values. If we drawing the PV diagram, depending on how you draw, it doesn't matter. Usually we write depending on how let's follow exactly how we write here the equation. So if I write this way, V proportional 1 over P, then let's make a graph V onto y-axis, P onto x-axis, okay? Doesn't matter actually, because we just check in the proportionality. You can do that graph any way you like. It's not really much problem at all, but I'm going to put pressure into volume into y-axis and the pressure into x-axis. Click OK, click OK again. We're expecting the inverse proportionality, right? So that means it should, when the volume decreases or the volume increases and the volume decreases depending on how these two behave, I'm expecting some sort of exponential decrement, right? Rapid decrement. Should not be linear at all. So we have fairly decent curvature here. That's good enough, I think. This going to be then volume versus pressure. Chart title, and also you need to add the axis title, right? Double click on the chart, left hand side very top, chart element, axis title primary, axis title vertical, and we can try to fit this maybe exponential negative to the power 2 or the power low. We might not be able to get the good curvature or the good fitting. That's okay. Fitting is not important at all. We're not going to calculate anything, okay? If the real numbers are there, actually we could do calculation like maybe if we know how many number of moles there are, and then we already know the temperature. If we have all the values, we could check maybe the ideal gas constant, but we can't do any of those calculations. Okay. Axis title horizontal is our pressure. Pressure we have 10 to the power plus 3, and then Pascal, the unit. Pressure and the unit. And your y-axis is the volume, and the unit for that is 10 to the negative 27 meter cube. Okay. Question. Now let's take a look one more type of graph. If I have an inverse proportionality here, I can make this graph linear by changing my x-axis. So instead of x-axis just pressure, let's do x-axis 1 over pressure. So the 1 over pressure mean in terms of unit 10 to the power minus 3, 1 over Pascal. Okay. 1 over Pascal. Let's do that, which means equal sign 1 divided by pressure D11, and then click and drag. We copy paste that function that is right here. This is 1 over P. Let's make another graph to see how the behavior look like. Insert, chart, scatter plot. Now I'm interested to see graph volume versus 1 over pressure. Okay, double click, select data, and now for x-axis we're going to use 1 over pressure, y-axis we're going to use volume as itself. Okay, C11 through C16. Now if all correctly done, then I should get a linear behavior. Okay, that's what we expected. Now you can see it's consistent and then very linear behavior, because what we're really doing is changing the view or the observation of this graph. Okay, that's all we did really. There's nothing else there. We're just observing how the behavior should look like. So the one graph is the Boyle's law is V proportional 1 over P. That's what we're observing on the graph 1. Okay, that's good. So as the volume increases, the pressure decreases. As the the volume decreases, pressure increases, right? So that's what we're observing on the figure 1. And figure 2, what we're doing, we actually selecting this into our y-axis. If you select whole thing into your x-axis, which means x is equal 1 over p, if you do that, then you should get this as a linear behavior. So that's what you're observing in your graph too. Now this is V, but this one is 1 over P, not just pressure, okay? So that's what we're observing on graph number 2. You have to name this properly, okay? Graph 2, axis title, primary, axis title, horizontal primary, and the vertical primary, and the chart title, you can say this is volume versus 1 over pressure, or you can say inverse pressure, either is fine. Now this is going to be 1 over pressure. Unit should be 10 to the power negative 3 and then 1 over Pascal. And this axis unit should be volume as previous case. Volume unit should be 10 to the power negative 27 meter cube. And in your report, you have to discuss, okay, what you're observing on figure number 1, what you're observing on figure number 2, and then so on, okay. And also for the procedure section, you should take a screenshot. Any questions so far? I'm going to take a screenshot by keeping a little bit of large volume here. That is screenshot I'm going to add here for the moment, but you have to use them. I'm going to add somewhere here for the moment, but you have to use them on procedure section, okay? Insert illustration pictures, then you select on your device. Usually those goes to the screenshot if you have a Windows machine. If not, you need to find that on the pictures, okay? Then crop that out, anything unnecessary, and then leave it only the area which our simulator we are using. Other area we don't need. Okay, so that our picture for this simulator, okay? And those pictures should go into procedure section, and then you should write a procedure in like bullet form, couple of sentences for each case, okay? Question. And also name these figures. Figure numbers goes continuously, right? That means if you have a certain number of pictures on your procedure, this may not be the figure 1, right? So you have to be careful with that numbering, but I'm going to assume this is figure 1. Then you can say this is the graph of volume versus pressure. Okay, and then similarly name every graph. This you can say for the moment figure 2, but make sure you check those numbering, okay? That depending on how many figures you have before, this is going to be volume versus 1 over pressure. Okay, question. Okay, then let's continue. So two graphs are good. Boyle's law is confirmed. Then we can slowly take a look at the Charles law. Any question? Okay, then let's continue and then take a look at the Charles law, and then these functions, you should not copy paste directly into the data section. That's not good, okay? Data is only these tables and these graphs, okay? Those are going to the data and analysis section, only that. And any calculation you want to show, like the equation point of view, then you can add those things. But these functions, I would suggest you could actually, if you want to, add the function too, but under the graph, okay? but you have to tell what calculation it does. You can't just put a function. Instead, you have to really write it down the sentence, the inverse pressure calculated by using this function, volume calculated by using this function, and then so on. Or you can use them on your discussion directly. That's also fine. Since we're not using the calculator any longer, I would suggest show those functions. That's part of the lab work, right? Then let's take a look at the Charles law. Any question? All right, and then let's continue. We can do quick look what happened if I change the charge, the type of the particle. Now we are using lighter particle, okay? If the time remaining, we'll come back and then check all the calculation with the heavier particles, okay? But let's take a look the Charles law now. Keep the amount of particles you added into the container as it is. Don't need to change that. We can use actually same amount of gas. So if you want to do the Charles law, if you remember that in the kinetic theory, so I have to keep the pressure constant of the gas container, and then I have to change the volume, or I have to change the temperature and the measure the other state variable, right? Either volume, what we're expecting is volume versus temperature should be linear behavior, okay? That's what we're expecting. So, which means I have to tell this program to make the pressure constant, right? I have to tell now we are on part B, okay? Question? Okay, then let's continue. So we have to tell keep the pressure constant. And temperature will change. And let's change the volume and then see. You have to click actually pressure constant on this last icon, okay? Not the middle icon. So there's two icons to keep the pressure hold. You can see there's two icons. One says the pressure and arrow and the V, and the last one says the pressure arrow and T. Click the last one, okay? Pressure arrow and T, because I have to physically change the volume and then I have to measure the pressure, okay? So that's the plan. Temperature should hold constant. Now let's see, we are starting at 5 nanometer. That's okay. We can go from here to up, or we can click this and drag all the way to the other end and then click it backward. That also possible. Let's see how much the pressure is changing. Anything? No. So we are good. So we can do that way. Let's go all the way to the maximum volume and then bring it back slowly. Maximum volume temperature is about 900 K. And you can see it's very looks nice in terms of sig figs. If I just use 900, I'm going to use 900.0, okay? Otherwise, it's going to look like just one significant figure. Looks bad, okay? And in the unit, it's better to put it on the top. We are using unit Kelvin. And similarly, this is unit on nanometers. And the volume, you know, volume we have to multiply all three dimensions. This should be 10 to the negative 27 meter cube, okay? Let's do that calculation also, equal sign, or you can copy paste these numbers which you done earlier. Either works actually, because it's the same numbers for the volume. We're not going to change at all, okay? If you want to copy paste from the previous, click and drag to select this range of cells on your column number C, cell number 11 through 16, and then paste it. When you're pasting, you have to be careful. That's a calculated value. You have to right click and then do paste special, okay? Select it, copy, When you're pasting, you have to right click and then paste is special values only. Otherwise, it will not. Otherwise, it may give you just the hashtag sign or something like that, or maybe the error. The numbers will not show correctly. Okay. And also last column, I would suggest to add at least one decimal place, because otherwise significant figure point of view, that looks very bad. It look like has only 1/6. Okay, question. All right, then continue. Then you know what to do. Now we are on the maximum volume which we can get with this simulator, and then we'll slowly decrease and then see what will happen to the temperature, right? That's all really. So we click this handle and then bring it to 13.0, and new temperature is 781, and to 11 nanometer in width, and new temperature is 660, then 9 nanometer in width, new temperature 539, 539, then the next volume number 7 nanometer in width, and new number is 421, new temperature, and the last number we can go is the 5 nanometer in width, temperature is 300. Okay, question. All right, then let's make a graph to check the behavior of pressure and temperature, volume and temperature, right? So let's make a graph. Insert, chart, scatter plot. And in this case, I need the data, double click, select data on right hand side top corner, and the add a new data series. So X values, in this case, I'm going to use temperature, and then Y values, in this case, we're going to use volume, and then click OK, it should be linear. Only we testing the behavior, okay? We don't need to fit this data or anything, but if you want, you can add the trend line, nothing wrong. But the numbers, equation or anything is not important at all. We can't really do any real calculation at all, okay? Only thing in the discussion, you have to discuss whether you observe the behavior, what we expecting from that particular gas law. If so, then write up couple of sentences about it, okay? Small paragraph for each table and each graph. If you have a graph, then make sure you name it properly. This is going to be then volume versus temperature, right? And also I need axis titles, left hand side very top, axis titles, primary, horizontal, and the vertical. Now the horizontal is temperature, right? Temperature unit should be Kelvin, and the vertical should be volume. Unit is same as for the previous case. Volume, this should be 10 to the power minus 27 meter cube. You can see I did not bring that 10 to the negative 7 into anywhere on these numbers because it's not meaningful. It's a really big, really small 10 to the power value. Because of that you have to keep it as a constant. Then when you draw the graph, just use it on with your units. Then we know all the numbers right here should multiply by that number, right? So that's easy. And do we have the right behavior of the law? This is going to be then figure 3 on my case, but on your case, you have to check the number, okay? It's going to be then graph of volume versus temperature. Okay, equation. And I had one graph earlier here, two here, and then this I name it as a third, but make sure since you're going to have a couple of simulator pictures like this one on your procedure section, the figure numbers should be different, okay? And should I want to take another procedure picture? I think you should, because this procedure is different. I'm holding the pressure constant, and then we measuring the volume and temperature, even though it's the same simulator, but for the procedure, it's completely a different approach. You should take another picture of this one, okay? Screenshot. Question. Okay, then let's continue. Let's take a look at the next part. Any questions so far? Okay, so the part number C, we're going to take a look how the temperature behave with respect to pressure. Good, any question? Everyone okay, right? Okay, then let's continue. Now I want to measure temperature as a function of pressure. Volume should remain in constant, right? So we can use the same, this is smaller gas cylinder now, or we can use a large one. Doesn't matter actually which one use. We'll use the large one. Now the volume must remain in constant, right? So volume remaining constant, and then I should add gases into the system and then increase the pressure slowly and then measure the temperature. That's the plan. Okay. Question. Okay, let's check that. So now I have a temperature 900. Pressure is about like 1089 kilopascal. So let's increase amount of pressure and then see whether the temperature is changing. You can see temperature is holding fixed, nothing changes, okay, if you do that way. So there's another way to do it. So let's bring this back to make it, if you want to get rid of everything, there is a yellow button right here on your right hand side, very lower, so that can reset everything, okay. So I reset everything, maximum volume, little bit of gas in, and then let's hold the temperature like we done for the first part. I want to see how much temperature is increasing. Pressure is increasing, not enough. Let's see in the kilopascal. Yeah, that should be enough, I think. That's fine. Now what we need actually hold the volume constant and then pressure versus temperature, right? So the best way to do this part right here, you can stay like the, doesn't matter actually which volume you use, okay? If you want to stay on the largest volume, that's fine, but make sure you noted them down. Or I can stay on the smallest volume. So let's say somewhere in between. Let's measure what number I'm using, maybe like 8. or 7 nanometer in width. Now you can see this container below, right? So that can actually change the temperature. Now I need to keep the volume fixed and then measure pressure as a function of temperature. Let's see, let's increase this one a little bit to see how much pressure is changing. See that? Now if you click this and then drag upward, then you will see like flames comes out the container. As a result, you can see temperature increases. As the temperature increases, you can see the pressure also changing, right? And then similarly, if you click this downward, you can see temperature decreases. I can cool it down all the way to close to absolute zero, I think. It's a simulator. You can go all the way to the absolute zero if you want to. So that's the plan, okay? The pressure we need to measure as a function of temperature. Now, the problem is that you can see it actually changing very rapidly. So you click this up a little bit and then hold it. You can see number is changing. You have to observe the Kelvin number here, okay, on top of the thermometer. And then we need to stop after it reaches a certain number. Let's say I want to read pressure at 100K. Then keep hold it close to 100K. Then stop this. Stop the clicking and then dragging this icon right here on the container. Then the temperature will hold. After the temperature will hold, you can extract the pressure value at that temperature. You can see still it's changing, right? It's changing by large number. So because of that, we have to maybe goes with the pause mode here. If you have the play mode, then that number is actually continuously changing. It's really not anything meaningful, because that change is so big. If you take a look, it changed like maybe sometime 50 kilopascal also up and down. May not be a good idea. So I'm going to go in with the pause mode, okay? Question. So which means I'm going to pause it, extract the number, then play it, then increase the temperature, extract the number again, okay? It will matters, I think. It may not matter since we observing only the ratio, only the variation. It might not matter at all, but it seems to be very unrealistic because the amount of change is very large. Not really anything is small numbers. So which means after reach a certain temperature, we can stop the play mode and then extract the pressure and then play it again and then change the temperature into next value, pause it and then read the pressure and then continue. That may be a little bit of consistent way of taking that measurement, okay? All right, so let's do that now. To do it, we can maybe start at 100 Kelvin, then we can go maybe 200, 300 or 500 Kelvin, each 50 Kelvin at a time, okay? Yeah, volume technically doesn't matter. You can add those information. I would suggest add those information into the table right here, because in the discussion section, you can use it. Now I'm using, for example, volume is I'm using 8 nano for the width, which means it's going to be 10 times 5 times 8, and then unit going to be 10 to the power negative 27 meter cube. You can keep that information because that will be useful when you do the discussion part, okay? Temperature we measuring at Kelvin, and the pressure we measuring at 10 to the power 3 Pascal, and we're going to take a look the P over T ratio, because if it is behave as it's supposed to be, P over T should show us a constant ratio. So that's the plan, okay? It might not in the numbers, but that's okay. Still we can get the right behavior in the graph, okay? Let's check that too. Now this would be then 10 to the power 3 Pascal over Kelvin. It's better to use here the square bracket. We always use that to represent the units, okay? All right, question. We can start like 100 Kelvin and then we'll increase the temperature each maybe 50 Kelvin, even 100 Kelvin, doesn't matter actually. So 100 Kelvin, we can take maybe 292. That's why these numbers will very difficult to do any, a realistic calculation with this simulator. It's not really much meaningful because you can see that change is so large. And let's do 150 to see what it is. Click and drag and then hold it. And then when it reach very close to 150, you can let it go. Then you may not be able to get exactly 150. That's okay. That's nothing to worry. Okay. Whatever the number close to that, just stop there. Then instead of writing 150, write the temperature value you observing on that thermometer. Okay. I'm observing now 152. Pressure is 372. Don't write the 150. Instead of you have to get exact number there. Okay. And then the same thing, then the plate, and then click this up and then heat it to close to 200. When it close to 200, you can stop and then read the pressure. When you're reading the pressure, read it on the pause mode. Okay. Going to be now 200 exact. Pressure is 463. And then same, play again, because without playing you can't change the temperature. That's a problem. Okay, you have to really click the play button to change the temperature. Then I'm gonna go into maybe 250. If you can't reach the 250 exactly, that's okay. If you cross that, whatever the number close to that, I have here 252. Okay, I'm gonna use that. Simulator should be on the pause mode, 592. Next one, 300. Pause mode, and the value is about 741. Next number, 350. If you can't get exactly 350, write it down, the number, whatever the closest number. Okay, 896. Would not matter much actually. There will be a little bit of error, but since we're not really calculating anything directly, it would not matter even. We can only see how the variables are behave each other. That's all. Okay, so last one we can do. You can take as many data as possible. Data point, that should be good enough. I think play mode. Increase the temperature to maybe 400. Close the 400, that's okay. We'll use 409. And the pressure is about 1028. Let's take a look whether we can get this calculation correctly. We might not get the constant value at all, but that's what we're expecting, right? The volume remaining constant. We can see whether the pressure and the temperature behave as it's supposed to be. Let's do this calculation. Equal sign temperature versus pressure. Not the temperature versus, sorry, equal sign. The pressure number divided by the temperature value. And then let's click and drag that cell to see the number, whether it's consistent or not. It is actually consistent, but there are a couple of data points you can see goes up and down, right? So it's about like between 2.5 and 2.9, little bit of variation, but not much. Compared to it, this is a very large number, 10 to the power 3 value, it's still consistent. We're not going to get exact numbers at all. Okay, question. Okay, then let's make a graph and then see how the graph look like. Let's make a graph P versus T. We are on part number C, okay? Let's make a graph pressure versus temperature and then discuss the behavior, okay? Insert scatter plot without anything, just make the graph sheet first, double click on the sheet, select data, and we are doing X into our temperature, and then Y is the pressure. It's a fairly consistent behavior. Okay, direct proportionality. There's one or two data points little bit off from the line, but that's fine, I think. Question. Pressure versus temperature can be the topic. And I need axis titles. Left hand side very top, axis title primary horizontal, primary vertical, same thing. Make sure you do all of those before you make the report. What we do in axis horizontal is the temperature. Unit Kelvin. And the vertical axis, pressure, unit going to be 10 to the power 3 Pascal. Okay. Yeah, yes, yeah. I think in the procedure section, you can add one screenshot for each procedure and then write up a little bit of procedure for that one, what you done, how you done that part, because it's same simulator, but there are differences. We using a different different parameter to fix, different parameter to change for each case, okay? So I would suggest take the picture for each case. This case, we already took one earlier, but the second case I did not, but you have to, okay? Table number 2, you have to have one, and then table number 3, you have to have another one. Okay, question? Okay, then let's continue. So table number 4. So in the table number 4, what we're trying to do, we really not trying to do any calculation, okay? Calculation going to be not possible to do, but we can take a look couple of other things in the kinetic theory. Anyone else has any question? In kinetic theory, if you remember, so we done a couple of other calculation, right? So we use the basic idea of the pressure from the physics 1, and then we calculate the pressure, and then we confirm that the kinetic energy is actually depending only on temperature of the system, right? So we can check that whether that is the case. If that is the case, average speed of the gas molecule should be behave as a function of temperature. That we can check with the simulator. We can't do calculation. It will do internal calculation and then show us the numbers, but we can check that whether it's behave the right way, the proportionality or not, okay? All right, now let's see. For that, we have to use the energy. There's 4 different options, right? So out of those 4, let's take a look now. We are on the part D. So the part D, I have to use the selection energy, okay? Option energy. So let's see option energy right here, third one. And then you can see the same container, same amount of gas, and then so on. And then I can check all of those things. And right here you can see average speed. So depending on the gas temperature, we can actually check the average speed behave as it's supposed to be or not. Okay, so that's one simple calculation we can do here. Okay, any question? We can use the same type of gas particle. So let's use the gas particle type, this red icon right here. Those are the smaller or the lighter gas particle. And then in this case, volume going to be fixed, right? We can keep the volume as it is. We don't need to change that at all. Gas particles are light, the orange color. And then let's add a little bit of gas into that. Let's change the pressure into kilopascal. And you can click this icon also. You can see the left hand side, there's two icons, how the speed is changing, how the kinetic energy is changing. Now that shows you the gas particle we are observing this orange color. Now every gas particle doesn't have the same average speed. The gas particle has a very, very different speed. And then if you take a look how that graph that look like little bit of Gaussian curve, but it's not exactly Gaussian curve either. So it has a middle portion where the average velocity of the gas particle, most of them has the same average, then it disappears on the both side to zero, almost close to zero. So very different type of behavior. However, if we calculate the average gas particle speed by using the same theory we done earlier, so we should get about like 1200 meter per second. So that's the number it calculated value actually shows you here. Now, what we can do, we can keep the volume constant and then change the temperature of the gas container. If I change the temperature, the pressure will also change. And then accordingly, we can check what will happen to the particle speed as a function of temperature and also as a function of pressure. Okay, so that's the plan. Question. Okay, and also that information in terms of your discussion, all those information you can find on your equation number 14. If you go to equation number 14, VRMS, root mean square speed of the gas particle, should behave directly proportional with the temperature. Okay, and since we're keeping the volume constant, if I have something proportionality with the temperature, if you use the PV equal in RT, then this same particle speed should be directly proportional to the square root of the pressure too. So that's the two information we can check here. Everything else remaining constant is the same type of particle. Kb is a constant, T is a constant. So this is the only variable I can have, okay? Temperature or pressure. Let's measure temperature in Kelvin, and the square root T gonna be the square root of Kelvin, right? So I can say Kelvin to the power half, and pressure gonna be same 10 to the power 3 Pascal, and the square root of pressure I can say 10 to the power 3 Pascal. I can put the square root outside. That is easy. And then VRMS gonna be meter per second, all the units. And then all we have to do now, slowly increase the temperature. Maybe we can start, let's cool this down a little bit to maybe 100. We don't need to go really low or really high. We can start maybe 100 and then go to about like 300, because then we can see how the behavior look around room temperature. Okay, let's start at 100, and then again the same. You can see the numbers are varies, right? Particle speed varies little bit, but the pressure is varies much. Because of that, you have to read when you're reading those data, you have to read in pause mode. Okay, now it is on play mode. Click on the pause mode, and then let's read the data. Temperature is 100, and the square root temperature we can calculate later. Pressure is about 229, and the square root pressure we can calculate later, and average speed, which is 704. This calculation we can do later, okay? And then we'll proceed. It's the same thing technically, okay? And then what we have to do then, click on the play mode and then increase the temperature by about 50 Kelvin. Increase, and then when it reach 50 or close to 50, doesn't need to be exactly 150, okay? I have about 105.4, that's totally fine. And then pressure is 262. We should know that it should increase with the temperature, right? And the average speed, you can say 884. Now you can see that should be some sort of the increment on both. Temperature increases, pressure should increase, we have seen earlier, and also the root mean square value of the speed must increase, okay? And it's the same thing again, like we done on the previous case. You have to go into the play mode and then increase this by another 50 Kelvin or so. And then go into pause mode and then read it. 202 I have temperature, pressure is about 361, and average speed about 997. And go back into the play mode, and temperature 250 we need now. Temperature 251 I have there, pressure is about 523, and average speed about 1138. And then let's continue another 50 Kelvin. 303. Temperature, pressure is about 553. Average speed about 1254. Play the simulator, another 50 Kelvin. 353. Pressure is about 659. And the average speed 1320. Another 50 Kelvin temperature increment. 405. Pressure is 804. Average speed is about like 1404. Okay, question. Now our plan is to check whether this behavior is correct or wrong, right? If the theory is correct, we should get VRMS directly proportional to the square root of temperature. Since the temperature is directly proportional to the pressure, the VRMS should be directly proportional to the pressure square root, right? So we can check the both. To check the both, I need actually first calculate the square root here. Equal sign SQRT, parentheses, temperature value, close brackets. Then you will get the square root temperature. So each different type of calculation you have to show that work, okay, or use it in the discussion. So this is how I'm doing the square root of temperature. And say t to the power 1/2. And then the pressure also we can do the same way, equal sign SQRT and the pressure value. I'm keeping the unit as it is separately, okay, because that's a common parameter. So I do the same way like we done for the temperature, pressure to the power 1/2. Now we need to make 2 more graphs. Question. Okay, then let's continue. Now let's take a look. Two more graphs. I need the graph sheet, insert, scatter plot, and then let's make a one graph V versus VRMS versus T to the power root. Double click, select data, and I can use x-axis is our square root temperature. Cell number C55 through 61, and then the y-axis, let's use measured particle speed, VRMS values. If that is correctly done with the theory, then we should get the linear behavior. That's what exactly you see. Okay. So in your discussion, that's what you have to discuss. What's the theory behind it? What theory is actually suggesting whether you're observing that behavior or not. We can't do any other calculation with the simulator. Okay. This is VRMS. You can say average speed, average molecular speed versus square root of temperature. Okay, and I need axis titles, horizontal, vertical, and then let's do that. Axis titles, T square root, you can just write square root of temperature. Any question? And then in units, you have to say Kelvin to the power half, right? And then similarly here, y-axis. Average speed, we have meter per second. Okay, so the same graph you have to make for the square root of pressure, right? So there's various way you can do graph. If you have one and then just need to change the data, then you can actually copy that graph or duplicate that. You can just copy paste that and copy and paste into somewhere. See, copy and then paste into a different location and then edit the data. That is much easier then. You don't need to really make the graph new. Instead of make a duplicate of the previous graph and then edit the data. To edit the data, you can actually only change the axis, y-axis, or you can just select data here and then remove the series 1 and then add that, or you could edit that even. Okay, select data and then you can edit that. So now what I need is to change just the x-axis, right? Y-axis remains the same. X-axis must be now pressure square root, right? So that should be this. Yeah, then we have a little bit of couple of data points go up and down, but the overall behavior remains there. Okay, now I just need to change only this one. Instead of square root of temperature, now this is square root of pressure. So it's much easier than just remaking that whole graph again, right? It's going to be 10 to the power 3 times Pascal. We can put the square root outside. So then it's much easier. You have to rename, okay, all of these graph. This is going to be now figure how many graph we had: 1, 2, 3, 4, and this is fifth graph. Okay, this is fourth graph. Earlier case we had the pressure versus temperature. Pressure versus temperature. Now we have a new graph here. This will be now. You have to name it properly. Okay, I'm not going to name these two, but you have to name those properly for your report purposes. Okay, I'm going to leave it empty. Here this is going to be figure number 5 according to my numbers, but those figure numbers also should be different for you, okay? Should not be the same. It's going to be 6th figure. Okay, question. And also only couple of functions, right? There's 2 functions here. There's no particular function for the previous. It's just only the division. You can call it if you want to as a function, that one too. This is how I did the P over T. Yes, title also you have to change on the last graph. Since we copy paste, this should be square average speed versus square root of pressure. Yep. And in terms of function 2 for last table, yeah, you need to take the new, this one you definitely take the new screenshot because it's a completely different apparatus than the previous. Okay, you need the new screenshot for this one, and you need 3 screenshots previously. Then there's 4 screenshots, 4 figures, which mean this figure should be start with number 5. So this should be number 5, 6, and then so on. But in terms of graph, this is our graph number 1. Okay. The screenshot has to go into the procedure section. The screenshots are not data, okay? Those should go into procedure section. Okay, question. All right, now this is what we're going to do. Since this lab is very short and easy and then very sweet, then we're going to start next lab. Reason, but you don't need to write 2 lab report, okay? Lab report going to be extended 1 week for the next one. But I think we can finish half or maybe the whole next lab too, probably at least half definitely, because we can save some time at the end of the semester that way. The reason why I would like to do it, our other section going 1 lab actually in front of us. They are in our lab. This week they're going to do lab number 5, I think. We are in the 4th lab, right? So if we do this lab, let me go into syllabus very quickly to show you why that is advantage for us. Let's see, now this is where we are, right? Gas laws right here. So now they're supposed to do, they're going to be 1 lab in front of us after exam number 2. Because you see, we are planning on doing the experiment on 12/14, just 1 day before, 2 days before your final exam. If we try to finish the 1 lab in between, we can actually make this day empty for the review session. Okay, so that will be very useful. So let's try that. We'll do half of that lab today, keep that data, and then if the time is not enough, we'll try to do other half maybe next week or maybe following week. That way we try to save this day for the review session, or if you have any last minute question, that will be useful. And then in terms of labs, you're going to be on the same speed as the other section. So that's the other advantage. So let's start next lab. Let's take a quick break, maybe 10 minutes or so. And then let's talk about next lab is actually, we did not do that part still in our lecture class. We have to go a little bit slower. I will explain you what we trying to do with the lab, how it is connected to the next chapters we are planning on doing. It's not very difficult since we're using these simulators. It's very visual and then very easy to do. Let's try to finish that, at least half of that, okay? Okay, let's take a break.